Everybody, let us talk about Shor's algorithm, which is one of the very important quantum computing algorithms. Now, in this algorithm, factoring a large composite number, capital N, is hard for classical algorithms. Suppose you are given a composite number, a large composite number N. So, if you want to find out the factors of this number, then for classical algorithms, it is a very hard job. Now, because of this hardness, the public key cryptography relies on this hardness because it takes the advantage that it is very difficult to find out the factors. So, public key cryptography uses this hardness in developing a secure cryptographic algorithm, which is used in many banking systems and other security related issues. So basically what I want to say is that public key cryptography relies on this hardness because factoring a large composite number is very hard for classical algorithms. Now Peter Shor gave an algorithm which is known as Shor's algorithm, and he simplified this job to a great extent. Actually, he used the quantum computing techniques to reduce the hardness involved in factoring the large composite number. Now, Shor's insight is that factoring can be reduced to a different task that is accessible to a quantum computer. Now, Shor's algorithm is based on offloading the task of factoring to first of all to a new type of task which can be offloaded to a quantum computer. Now, the factoring of a large composite number, Peter Shor actually reduced it to order finding, the period finding algorithm. I have already made a video which explains the period finding algorithm. So you will have to refer to that video in order to get the details of what is the order finding algorithm and what are the details of that. But as far as the context of the Shor's algorithm is concerned, I will describe in this video. Keeping in view that we will find out the period of a function using the algorithm which I have already explained in one of the videos. Now, how the Shor's algorithm goes: pick an integer. So let us choose an integer a with values between 1 and capital N, and let's say the greatest common divisor of a comma n is 1. The order r or the period r, I will specifically call here as the order r of a mod n is the smallest positive integer such that a to the power r is congruent to 1 over mod of n. Let me first explain I will as I will go along with the lecture, I will explain the basic fundamentals needed to explain this algorithm in more and more detail with examples. So what is the meaning of a to the power r congruent with 1 over mod n? So what it means is that if I divide a to the power r by n, and if I divide 1 by n, the remainder in both the cases will be same. That's the meaning of congruency. Or in other words, I can say that a to the power r minus 1 is divisible by capital N. So that's the meaning of congruency. Now, further, if this is the case and if we know such an r, so if this is the case that a to the power r is congruent with 1 over mod of n, actually what is the meaning of a mod capital N? The meaning is the remainder. So when I divide a by n, whatever is the remainder, that is the representation. This remainder is given by a mod n basically. Now if we know this r, which is the order of the function order of a function a to the power x mod of n. So let us say I know r. How I would know r? I will use the period finding algorithm or the order finding algorithm, which I just said that the algorithm is described in another video. So if I know r, a to the power r is congruent to 1, so I can check this equation, and if r is even with a to the power r by 2 is not congruent to -1 mod n. I will also explain the meaning of this line because this is important. And if these two tests hold, that means if I know r and r is even with the satisfaction of this equation, then I can find the factors. How will I find the factors? I will calculate the GCD of a to the power r by 2 minus 1 comma n and GCD of a to the power r by 2 plus 1 comma n. My as I just mentioned here that composite number capital N will have factors p and q. Now the first value will be p and the second value will be q. These are the factors of capital N. Now, and these are known as the non-trivial factors of capital N. I will also explain what are non-trivial factors, what are trivial factors also in just a moment. So therefore, the heart of the problem is to find the period r. So in Shor's algorithm, how Shor's algorithm is able to achieve the quantum advantage over the classical algorithms is that we are able to find out the period r of the algorithm using quantum ways. Now, so therefore the heart of the problem from which the Shor's algorithm gets the exponential speed up or the quantum speed up is because we are able to find period r in a quantum way. So period finding is exactly the kind of hidden structure that quantum phase interference and quantum Fourier transform can reveal. Now period r is the period of the function fx equal to a to the power x mod n. We will come to know more about this function as we go along with the lecture. Now Shor's algorithm is therefore a hybrid type of algorithm in which there is a quantum part and there is a classical part. What is the quantum part? Period finding. That means we have to find r in a quantum way. What is the classical part? Once we know r, we have to find out this GCD. We have to find out two GCDs which are actually the factors of capital N, right? So use GCD to extract factors from this period. Now let us now try to understand the basic and the fundamental concepts involved in the this is basically the overall Shor's algorithm. Now let us try to understand the fundamental concepts also. Now as I said, as I just mentioned here, factoring a large composite number. So let us see what is a composite number first of all. Now a composite number is a positive integer greater than 1 that is not prime. So what does it mean? For example, let me take the case of 4. Now 4 is a composite number. How? Because it will have factors 1 and it will also have factor 4. We know that any number can have these two factors. But if the number has factors other than these two factors also, that means 1 and the number itself. If the number has got other factors also other than 1 and the number itself, then that number is a composite number. Now 4 has got factors 1, 2 and 4. Now 3 is not a composite number because 3 has got only two factors, 1 and 3, but no other factors. So therefore 3 is not a composite number. 4 is a composite number because 1 and 4 are factors and along with 2. 2 is also a factor of 4. In the same way, 6 is a composite number because 2 and 3 are also the factors of 6. Like that, I hope this point makes what is the composite number clear. Right. Now, what are the key points as far as the discussion of the composite number goes? The smallest composite number is 4. Every even number greater than 2 is composite because every even number will be divisible by 2. So therefore, it will have at least one factor 2 other than 1 and the number itself. So therefore, every even number is a composite number. Composite numbers can be expressed as the product of prime numbers. So if a composite number is there, then it can be expressed as the product of prime numbers. Like for example, our problem at hand. For example, this is the composite number. It can be expressed as a product of two prime numbers, right? Odd primes. So this is actually the problem. That means we want to find out these two factors of a composite number capital N. Now let me read that statement which I was just trying to read. Composite numbers can be expressed as a product of prime numbers. So factoring a composite number into prime factors is known as prime factorization. So this is the goal of Shor's algorithm. What is the goal? Prime factorization. Factoring a large composite number into its prime factors. Now let us try to also look into the details of the greatest common divisor, although this is a school level concept, but let me particularly introduce every concept so that the things become clear if anybody needs to brush up the concepts. So GCD is known as greatest common divisor. Now there can be two types of factors. One is non-trivial factors and other is the trivial factors. Now what are trivial factors? Number 1 and the number itself. So therefore 1 and the number itself, these are the trivial factors. So any other factor will be a non-trivial factor. For example, in the case of 4, 2 is a non-trivial factor, whereas 1 and 4 are trivial factors. So non-trivial factors are the prime factors of a composite number n, which are neither 1 nor n. Right? Any other factor will be a non-trivial factor. So non-trivial factors are any other divisors p comma q such that n is equal to p into q. But p and q will the value of p and q will be between 1 and capital N. Now for two integers a and b, GCD of a comma b is the largest integer that divides both a and b exactly. That means with no remainder. So GCD of 15 comma 9 is 3. Let us try to look into how to find out the GCD of two numbers also. The algorithm used to find out the GCD is known as the Euclidean algorithm. Now let us see how the GCD is calculated for two numbers. Let me explain let me explain from the example, then I will relate the example figures with the algorithm. Now let us we have to find out the GCD of 30 comma 12. So so a is equal to 30 and b is equal to 12. That means we have to divide a by b. So that's the first step, divide a by b. Here a is 30 and b is 12. So we divide it, 12 2s are 24. So therefore quotient is 2, remainder is 6. So I can put out this equation, 30 equal to the quotient into b plus the remainder. So remainder is 6. So that is equal to 30. So that's the first division. First divisionary step, right? So then after the first step of division, we have to replace a with b. So that means now in the next step our a will be 12 and we have to replace b with the remainder. So in the next step our a will be 12, our b will be 6 because it has to be replaced with the remainder. So again the same thing. In this case the remainder will come out to be 0. So what is GCD? GCD is any non-zero, so is the last non-zero remainder. So what is the last non-zero remainder? 6. So therefore the GCD of 30 comma 12 is 6. And in the same way we can find out the GCD for 97 comma 13 also. Now how the GCD concept is used in the Shor's algorithm. Now case 1, pick a random A. So we have two numbers here. One number is capital N and another number in the algorithm. Let me just bring that. Okay, so as far as the Shor's algorithm goes, we have starting point is we have two numbers, capital N, and another number we will choose between A and N. That number is A. So therefore we have two numbers, A and capital N. P and Q we have to find at the end of the algorithm. So we have A comma N. Now let me come to the point. Okay, so we will choose, we know what is capital N. We will choose a number small a, which is the value can be anything between 1 and n. So we will compute whatever we have chosen. So we will compute the GCD of a comma n. If the GCD of a comma n is greater than 1, right? We have already found a factor. So no need to further go along with the algorithm. But if the GCD is equal to 1, we have to continue with the algorithm. That means we have to continue with the quantum part to find the period of the function, right? So first we will have to choose A and we have to then find out GCD of A comma, and if it comes out to be greater than 1, that means we have already found out the factor, which is A basically. But if the GCD is equal to 1, then we will have to continue with the Shor's algorithm. And the first step in the Shor's algorithm is the quantum step, in which we have to find out the period of the algorithm. So let us take this example. Capital N is 21 and let's say we chose A equal to 6. So we have to find out the GCD of 6 comma 21. The GCD comes out to be 3. It is greater than 1. So no need to further go along with the algorithm. We already found the factor and one of the factor is 3. So other we can find out. Now, what is case 2? In case 2, when GCD of A comma N is 1. So in this case, we will find out the period R using the quantum algorithm, and when we have found out R, we will check whether R is even or not. If R is even, right, and a to the power R by 2 is not congruent with minus 1 over mod n. I will explain this, the meaning of this, the value that comes out from this expression in just a moment. So if these two conditions are fulfilled, then we will compute these factors by computing the two GCDs, right? So let us do an example to find out the factors where n is equal to 15 and a is chosen to be 2. Find out the GCD. GCD comes out to be 1. So if the GCD is 1, we will have to continue with the quantum part of the algorithm, in which we have to find out the period. So the algorithm that I explained in one of the other videos, using that algorithm we found out that R comes out to be 4. So if now we know R also, so therefore we will find out two GCDs, right, and 3 and 5 will be our factors. P and Q will be 3 and 5. This is how the Shor's algorithm will be used to find out the factors of a composite number. Now let's go more into depth of some very fundamental concepts, like two integers a and b are co-prime or relatively prime if they have no common positive divisor except 1. So these are two co-primes. Like, why this is important? Because the factors which we have found using Shor's algorithm, they are co-prime. That means p is equal to 3 and 5. They will have no common positive divisor except 1. That's why the term co-prime is important. Now let us now understand the congruency, which is the heart of the operational concepts. If we talk about the most important operation is the congruency operation. So let us see fundamentally the explanation of the congruency. Now what is congruency in modular arithmetic? Modular arithmetic is a system of arithmetic for integers whose numbers wrap around after reaching a certain value called the modulus. So What is modular arithmetic? We will try to find out more numbers until we reach a final number, which we will call as the modulus. Once we reach to the modulus, the cycle will repeat. That means it is a system of arithmetic for integers where numbers wrap around after reaching a certain value, which is called as the modulus. So what is the meaning of a mod n? A mod n is actually the meaning is the remainder. For example, if I am given 10 mod 3, so what is the answer? I will have to divide 10 by 3. So what is the remainder? 1. So 10 mod 3, answer is 1. 17 mod 5, the remainder is 2. So answer is 2. Right. So that's the meaning of a mod n. Now two integers a and b are said to be congruent. Now if we are given two integers and they are said to be congruent modulo n. Right. This is how we write. A is congruent with b over modulo n. Yeah, or we can say a congruent b modulo n. So two integers a and b are said to be congruent modulo n if they give the same remainder when divided by n. So if a is divided by n and b is divided by n, both divisions will give me the same remainder. So these two numbers will be congruent, or equivalently we can say that once we find out a minus b, so that means n will divide a minus b. If this is the case, then a and b are said to be congruent. Right. So if n divides a minus b, I can write this expression a minus b is equal to k. K is any integer into n. Right. Now let us take an example in which let us check whether this statement is correct or not. That means 17 is congruent to 2 mod n. So that means if I divide 17 by 5, what is the remainder? 2. If I divide 2 by 5, what is the remainder? 2. So in both the cases the remainder is same. So therefore 17 is congruent to 2 over 5. Or if I find out the difference between the two, 17 minus 2 is 15. So that means 15 is divisible by 5. So therefore again the equation is true. That means 17 is congruent to 2 over mod 5. And these are some algebraic rules, like if A is congruent to B over mod n, C is congruent to D over mod n, then we can say A minus C is congruent to B minus D, or A into C is congruent to B into D, and A plus C is congruent to B plus D over mod n. So these are some extensions of the algebraic rules. Now let us try to understand the setup for the Shor's algorithm. So we know what is capital N, we know what is small a, that we make a choice. The value lies between 1 and n for a. We calculate the GCD, the order R. If GCD is 1, we will find out the order R. The order R of a modulo n is the smallest positive integer. So this is the formal statement of the Shor's algorithm. Like if GCD is 1, the order R, what is order R? Of a modulo n. So we are actually finding out the order of what? A modulo n, a to the power x modulo n. A modulo n is the smallest positive integer such that, so it will be smallest positive integer such that a to the power r is congruent to 1 over mod n. Right. So modulus has got the same meanings. Divide AR by n, the remainder is 1. So if we divide a to the power r by n, the remainder has to be 1, because then only the congruency will occur between a to the power r and 1. And we can also say that a to the power r minus 1, capital N divides a to the power capital R minus 1. So therefore I can write a to the power r minus 1 equal to kn for some integer k. Right. So now let us look at one of the very crucial observations. So if r is even, as this was one of the conditions, that if r is even, then of course I can write r equal to 2 into k, right? Any k multiplied by 2. So therefore I can a to the power r is congruent to 1 mod over mod n. I can write this as a to the power 2k congruent to 1. Then I can take the 2 outside from the exponent, and that gives 2 possible, because this is the square of a, so it will come out to be plus minus. Once I take this square off from here, it will come out to be a to the power k is congruent to 1, or a to the power k is congruent to minus 1. So 2 possible consequences will appear, right? So let us take an example. So the example says that capital N is 15. So we choose a equal to a equal to 2. The GCD comes out to be 1. So we will compute the successive powers, because if you remember, R was a period of function. Let me write here. R was a period of function a to the power x mod n. So therefore, we actually compute successive powers of 2, right? Compute successive powers of 2 mod 15. So this we have to compute actually. Let's see how. GCD is 1. So we will find out the order comes out to be 4, right? Once the order comes out to be 4, I will find out I can check, I will compute 2 raised to the power r by 2, which is 4, right? Let me just okay, take this. Yeah, this is the second equation. A to the power k is congruent to minus 1. Now let us look at what is this equation, right? So 2 equations are there. The first equation is a to the power r is congruent to 1. So this is going to be I can write it like this: a to the power r by 2 square. So I can put it like this: a to the power r by 2 minus 1, a to the power, because if I take the square off, plus minus will come here, and if I take plus 1 and minus 1 to the left hand side, I will get this equation, right? So n divides the product, but not necessarily each factor individually, right? So capital N divides this factor, but not so in this equation, capital N will divide the product but not the individual factors, like a to the power r by 2 minus 1 or a to the power r by 2 plus 1. Let us now do the full example actually. So capital N is 15, A is 2, GCD comes out to be 1, so we will have to find out R. To find out R, we will compute successive powers of 2 mod 15. So for k equal to 1, this comes out to be, the answer of this equation comes out to be 2, because 2 is the remainder. For k equal to 2, it is 4, right? So because see, 2 to the power 1 mod of 15 is what? 2. 2 to the power 2 mod of 15 is 4, and 2 to the power, okay, just a minute, let me just rub this so that the notes part remains legible. Okay, let me just have, okay. So for k equal to 1, the answer of this expression is 2. K equal to 2, the answer is 4. K equal to 3, the answer is 8. But for k equal to 4, 2 raised to the power 4 is 16. So answer is 1. So therefore this equation is satisfied. So when this equation will be satisfied, that will be our period, right? So check conditions. So once we found out the period, we will check the conditions. What conditions? That R is even, of course R is even, and we will check with this expression. That means 2 raised to the power r by 2. This is r by 2 is 2. So 2 raised to the power 2 is equal to 4. And we will check this second part, which is 4 is not equal, 4 is, this is not equal to, this is rather not congruent. 4 is not congruent to minus 1 mod 15. actually what is the meaning of, how will you prove that this expression is true? So let us check what is the meaning of minus 1 mod 15. So minus 1 mod 15 is the, of course it has to be remainder, is the remainder when you divide minus 1 by 15, right? So that's the meaning of this expression. Since remainders are usually taken as non-negative, you can always add 15 to minus, because the numbers will wrap around, because this is negative. So since, as I said, remainders are always taken as non-negative, so you add 15 here to this number. So this will come out to be 14, right? So minus 1 plus 15 is 14. So minus 1, this is 14. So in that case, let me just in that case, okay, so this is minus 1, minus 1, okay, this is not required, this line is not required. So minus 1 mod of 15 is actually 14 when we add 15 to minus 1, right? So therefore when we compare, because this expression must hold true, that means minus 1 mod 15 is 14, 4 is not congruent to 14, right? Compare 4 and minus 1 mod 15. We check whether 4 is congruent to minus 1 mod 15. So that means we have to basically check for what is the meaning of minus 1. Minus 1 is actually the meaning is 14. So therefore we have to basically check whether 4 is congruent to 14 over mod of 15. That means, how we can check this? We will have to divide 4 by 15. The answer is 4. We will have to divide 14 by 15. The answer is 14. So therefore 4 is not equal to 14. That means the two remainders are not equal. So the congruence is false. Hence our second condition is true. This condition we have to check. Let me just come back to the starting expression. This condition is also true, this condition is also true, and then we can find out the factors. I hope the processes and the mathematics is clear, that how to find out the factors of a large composite number. Thank you.